The telephone rang at exactly 11 minutes past 2 on that sweltering June afternoon in 1940. Highland Park, Michigan blazed under summer heat that made the air shimmer above concrete. Inside Chrysler headquarters, the building's brick walls trapped the warmth like an oven. William Knudsen gripped the black telephone receiver. Sweat beaded on his forehead, despite the building's industrial fans. Roosevelt's newly minted Commissioner of Industrial Production had a question that would sound insane to most ears. The words came slowly, deliberately. "Can your company build tanks for America?" On the other end of the crackling connection sat Kaufman Thuma Keller. Chrysler's chief executive leaned back in his leather chair. The question hung in the humid air between Detroit and Washington. His answer cut through pretense like a blade. "I honestly don't know." The admission stung. "I've never laid eyes on one of these machines." That brutal honesty captured America's military reality in 1940. The United States Army possessed exactly 66 medium tanks. Not 600, not 6,000. 66 tanks protected the entire continental United States. Across the Atlantic Ocean, Nazi Germany's panzer divisions had unleashed over 3,000 tanks across European battlefields. Poland had fallen in 26 days. France collapsed in 6 weeks. The mathematics of modern warfare were written in smoking steel and shattered concrete. Germany's armored columns rolled through Belgium like a mechanized avalanche. They crushed Dutch resistance in 5 days. They surrounded British forces at Dunkirk with clockwork precision. Each victory demonstrated that tanks weren't just weapons. They were the weapons that decided battles before infantry could deploy. America's entire tank force could have been destroyed in a single afternoon. One German panzer regiment possessed more armor than the United States Army. The comparison was embarrassing, terrifying, and absolutely true. Neither Knudsen nor Keller understood that their 7-minute conversation would trigger the most dramatic industrial transformation in military history. Within 9 months, Chrysler would achieve what no military arsenal had ever attempted. 30-ton steel monsters would roll off assembly lines like family sedans. One tank every 55 minutes at peak production. The concept shattered every assumption about military manufacturing. It proved that American industrial genius could weaponize mass production itself. The challenge began with a mathematical impossibility. June 1940 found the United States ranked 19th in global military power. Portugal's army was stronger. Argentina possessed more modern weapons. America's military had more horses than tanks pulling supply wagons. The War Department's Ordnance Section operated using production methods unchanged since the Great War. Tanks were hand-assembled in government arsenals. Each vehicle represented a custom creation requiring master craftsmen. Skilled metalworkers shaped armor plates by eye and experience. Rock Island Arsenal in Illinois managed perhaps 3 medium tanks monthly, working at maximum capacity. Each tank demanded 12 weeks from raw steel to battlefield readiness. Every rivet was hand-drilled. Every component was individually fitted. Every assembly step required specialized knowledge passed from craftsman to apprentice. Germany's panzer production followed similar artisan methods, but German manufacturers benefited from years of secret rearmament. Hidden factories had been producing tanks since 1935. By 1940, German industry delivered 1,400 tanks annually across multiple production facilities. Britain had mechanized faster than America after recognizing the armored threat. British factories managed 1,000 tanks yearly, despite shortages of steel and skilled workers. Every major military power viewed tanks as sophisticated weapon systems requiring master craftsmen and months of careful assembly. Tank production was art as much as engineering. Each vehicle was unique. Components required constant adjustment during assembly. Tolerances were loose because precision manufacturing was impossible with existing methods. Keller replaced the telephone receiver and immediately summoned his engineering team. Within 30 minutes, B.E. Hutchinson arrived at Keller's oak-paneled office. Frank Zeder, Chrysler's vice president of engineering, rushed from a design review meeting. The three men gathered around Keller's polished conference table. The Army wanted 1,000 medium tanks. They wanted delivery in less than 18 months. They expected Chrysler to build a factory, develop production methods, and deliver finished vehicles starting from zero tank manufacturing knowledge. Hutchinson's first question exposed the magnitude of their challenge. What's the current production timeline for a single tank? Zeder had researched military production methods that morning. Rock Island Arsenal produces 3 M2A1 medium tanks monthly, 12 weeks per vehicle. Skilled craftsmen throughout the process. Hand-fitted components requiring constant adjustment. Hutchinson performed the mathematics instantly. His engineering mind processed the impossible numbers. At current production rates, 1,000 tanks would require 277 years of continuous manufacturing. The Army needed them delivered in 18 months. Keller's response would define the entire program philosophy. We don't manufacture tanks using the Army's methods. We build them using our methods. If military officials want 1,000 tanks in 18 months, they must accept automobile production principles. Mass production, standardized components, moving assembly lines. But first, we need to understand what we're actually building. The trio visited Rock Island Arsenal within days. They watched workers hand-fit armor plates with hammers and files. Track tension was adjusted by experienced feel rather than measurement. Parts were custom machined during assembly to account for tolerance variations. The current production model was the M2A1 medium tank, a 19-ton vehicle mounting a 37mm main gun. Each tank required approximately 8,000 individual components manufactured to military arsenal tolerances that demanded skilled fitting during assembly. No two tanks were mechanically identical. Each represented a unique creation shaped by craftsman interpretation. Production was sculpture rather than manufacturing, art rather than engineering. Keller recognized the fundamental flaw immediately. This isn't industrial production. It's individual craftsmanship. Every component depends on worker skill and experience. You cannot scale artisan methods. Training new workers requires years of apprenticeship. Expanding production means finding master craftsmen who don't exist in sufficient numbers. Manufacturing 1,000 tanks this way is impossible within any reasonable time frame. The delegation returned to Detroit with new appreciation for the challenge. They convened what became known as the Tank Committee, a secret working group tasked with solving an impossible problem. The committee included Owen Skeleton, Chrysler's chief production engineer, plus specialists in tooling, metallurgy, and logistics. They commandeered a secured conference room at Highland Park. Meetings occurred daily, often extending through the night. Coffee cups accumulated on the polished table. Cigarette smoke clouded the air. Engineering drawings covered every wall surface. Their breakthrough came from reversing the fundamental question. Instead of asking how to build tanks faster, they asked how to build tanks differently. The insight would revolutionize military manufacturing. Skeleton articulated the revolutionary concept during a late-night session in July. An automobile weighs 2,000 pounds. Steel, rubber, glass, and mechanical components assembled from 5,000 individual parts. We manufacture 3,000 cars daily at Highland Park alone. A tank weighs 30,000 pounds. Steel assembled from 8,000 parts. The only difference is what we're assembling. The materials are similar. The manufacturing principles should be identical. This reframing changed everything about tank production philosophy. If tanks were simply another mechanical assembly, then automobile production principles could apply directly. But this required completely reimagining tank manufacturing from first principles. Every component needed redesigning for mass production tolerances. Every assembly sequence required re-engineering for line production. Every quality control step needed shifting from craftsman judgment to measurable specifications. The committee analyzed the M2A1 design with automotive engineering eyes. They discovered that 60% of production time involved custom fitting and adjustment. Parts manufactured to military arsenal tolerances varied so widely that assembly required constant adaptation. Military specifications allowed tolerances measured in fractions of inches. Automotive tolerances were measured in thousandths of inches. The difference represented the gap between craftsmanship and mass production. Hutchinson proposed the revolutionary solution that would transform military manufacturing. We manufacture every single component to automobile industry tolerances. Then components fit together without adjustment or modification. Military engineers considered this impossible. Tank components faced combat stresses exceeding automobile parts. Precision manufacturing at automotive tolerances would require new tooling, new suppliers, and completely new quality control methods. But total production time would plummet dramatically. A tank requiring 500 man-hours of assembly time with hand-fitting could drop to perhaps 150 man-hours with precision components that simply bolted together without modification. Skeleton expanded the concept further during August planning sessions. If we're treating tank production like automobile manufacturing, we need a moving assembly line, not workstations where craftsmen gather around stationary tanks. A continuous line that brings work to stationary workers performing specific operations. By November 1940, the committee had developed what they called the Chrysler method for tank production. Every major component would be manufactured to precision tolerances using automotive machine tools. Armor plates would be standardized and completely interchangeable. Hull sections would be welded using production jigs rather than hand-fitted by craftsmen. Turret assemblies would mount on standardized rings manufactured to thousandths of inch tolerances. Drive-train components would utilize existing automotive parts wherever possible. Final assembly would occur on a moving production line with specialized workstations. Each worker would perform specific operations as tanks moved past their position. Quality control would rely on measurements rather than craftsman judgment. Keller presented the Chrysler method to Army Ordnance Department officials in November 1940. Military engineers responded with skepticism bordering on hostility. Their objections came rapidly and forcefully. Automotive tolerances were insufficiently robust for combat vehicles. Moving assembly lines would create quality control problems impossible to detect until tanks reached battlefields. Welded armor construction was inferior to proven riveted methods. The proposed production rate of 10 tanks daily was pure fantasy. No military manufacturer had ever achieved such output. The entire concept violated established military production principles developed over decades. Keller possessed one irrefutable argument that silenced every objection. You need 1,000 tanks delivered in 18 months. We can manufacture them. Can anyone else meet that requirement? The Ordnance Department could not answer affirmatively. No existing military arsenal possessed the capacity. No private manufacturer had offered credible alternatives. Chrysler represented the only viable path to meeting urgent production requirements. Late November 1940 brought an unprecedented government contract. The Army would finance construction of a purpose-built tank manufacturing facility. Chrysler would design, equip, and operate the entire complex using their revolutionary production methods. The contract included one additional requirement that pleased Keller enormously. The Army insisted that facility design be handled by Albert Kahn, Detroit's legendary industrial architect. Kahn had revolutionized factory design through buildings that maximized efficiency and minimized construction time. Albert Kahn was 71 years old in 1940, a German Jewish immigrant who had arrived in Detroit during 1881 at age 11. His family fled economic hardship seeking American opportunities. Young Albert never attended formal architecture school, learning his profession through apprenticeship. By 1940, Kahn's architectural firm employed 600 architects and engineers. Albert Kahn Associates had designed 19% of all architect-designed industrial factories throughout the United States. Their portfolio included automotive plants, aircraft factories, and steel mills. Kahn's genius involved treating factories as precision machines themselves. His designs maximized natural lighting, optimized material flow patterns, and created column-free spaces allowing flexible production layouts. He pioneered reinforced concrete construction techniques that allowed larger open floors and dramatically faster construction than traditional steel frame buildings. When Keller approached Kahn about the tank arsenal during July 1940, requirements seemed mutually incompatible. The facility needed massive size to house complete tank assembly lines, plus component manufacturing areas. Construction had to be completed within months to meet April production deadlines. The building required bomb-resistant construction in case of enemy attack, and the entire facility needed conversion capability for civilian production after war ended. These requirements challenged every aspect of industrial design. Kahn accepted the commission immediately and devoted his entire firm to the project. Design teams worked 18-hour days producing drawings for what would become the Detroit Arsenal Tank Plant. The main building would measure 1.25 million square feet under a single roof. This made it one of the largest industrial structures anywhere in the world. The design incorporated 3-foot-thick reinforced concrete walls in critical production areas, thick enough to survive direct bomb hits without structural collapse. The roof structure featured reinforced steel trusses, designed to deflect bomb blasts away from windows and ventilation systems. Even enemy air attack couldn't halt production for extended periods. The facility layout embodied Chrysler method production principles perfectly. A main assembly line would run the building's entire length, nearly 1/4 mile of continuous production. Feeder lines would deliver major components to the main line at precisely timed intervals. Machine shops occupied northern sections, producing drivetrain components and precision parts requiring heavy equipment. Welding areas filled southern sections where armor hulls and turrets would be fabricated using production jigs. The entire design allowed materials to flow in one direction only. Raw steel entered at the western end. Finished tanks rolled out the eastern doors. No backtracking, no inefficient material handling. Pure linear flow from raw materials to completed vehicles. Kahn's plans included one innovation that military engineers had never considered. The main assembly line would be sunken below floor level, creating a concrete trench approximately 4 feet deep throughout the building's length. Tanks would ride on special carriers within this trench, allowing workers to access undercarriages without hydraulic jacks or maintenance pits. This single design choice would eliminate hundreds of assembly hours per tank by simplifying suspension and drive train installation procedures. September 9, 1940, brought groundbreaking ceremonies on 113 acres of former farmland in Warren Township, Michigan. The site was chosen for proximity to existing Chrysler facilities and direct access to multiple railroad lines for material delivery and finished vehicle shipment. Construction began immediately and proceeded at a pace that seemed dangerously reckless. Multiple contractors worked simultaneously, racing to pour foundations, erect wall sections, and install utility systems. Kahn's reinforced concrete construction methods allowed rapid building progression. Each concrete section cured sufficiently to bear structural loads within days rather than weeks. Construction proceeded in overlapping phases that maximized speed while maintaining structural integrity. By February 1941, the main building was structurally complete, but far from operational readiness. Exterior walls stood complete, but window installation remained incomplete. The massive roof was finished, but interior systems including heating, electrical, and compressed air remained under construction. Despite incomplete construction, Chrysler began moving production equipment into the facility. Machine tools arrived by railroad and were installed even as construction continued around them. The timeline created impossible working conditions that winter. Keller faced a critical decision in March 1941. Chrysler had committed to delivering the first production tank by April 1941, but the factory wouldn't achieve complete readiness until May at earliest. Weather remained brutally cold with frequent snow and freezing temperatures. His decision became legendary throughout American industry. "We'll build the first tanks inside an unfinished building." This created working conditions that bordered on the surreal throughout that final winter. Michigan's February and March climate is notoriously harsh. Temperatures often plunged below freezing for days. The Detroit arsenal possessed walls and roof coverage, but no functional heating system and incomplete window installation. Workers assembled precision machinery while wearing heavy winter coats. Their breath was visible in frigid air as they performed delicate operations requiring steady hands. The solution was improvised but remarkably effective. A steam locomotive was brought inside the cavernous building. Its coal-fired boiler provided localized heating to immediate work areas. Steam pipes were run throughout the assembly floor, creating pockets of warmth where critical operations could be performed. The image captured the entire program's determination. A steam locomotive belching smoke and steam inside a factory building while workers assembled tanks nearby. This wasn't careful industrial planning. This was sheer will-forcing reality to accommodate urgent requirements. Meanwhile, the tank committee continued solving technical challenges that would have stopped traditional military production. The drivetrain presented the first major engineering obstacle requiring complete redesign. The M2A1's transmission system was designed for hand assembly by skilled craftsmen. Each unit required individual adjustment and testing during installation. Chrysler engineers redesigned the entire system using automotive mass production principles. Their new transmission could be assembled on a dedicated production line and installed as a complete module without adjustment. The redesign reduced assembly time from 40 hours per tank to 4 hours, a 10-fold improvement in productivity. The suspension system required similar fundamental rethinking. Military suspension components were manufactured to loose tolerances requiring skilled fitting during tank assembly. Chrysler engineers standardized every component and created assembly fixtures that allowed pre-assembly and testing before installation. A complete suspension assembly could now be built in 2 hours on a dedicated line and bolted to the hull in 20 minutes. No adjustment. No skilled fitting. Pure plug-and-play installation using precision manufactured components. The armor hull presented perhaps the greatest technical challenge requiring revolutionary approaches. Traditional tank hulls were riveted together from multiple steel plates. Each rivet required hand drilling and installation by skilled workers. This process consumed weeks and created structural weaknesses. Rivets could shear under combat impact, spraying deadly metal fragments inside crew compartments. Every rivet represented a potential failure point under stress. Chrysler proposed all-welded hull construction. Military engineers objected strenuously to this radical departure from proven methods. Welded armor had never been combat-tested under battlefield conditions. Welding created heat stresses that might compromise armor protection. Welding required skilled operators unavailable in sufficient numbers for mass production. The objections seemed insurmountable. Chrysler engineers methodically countered each objection with testing and demonstration. They produced test welds that proved stronger than riveted joints under ballistic impact testing. They developed heat treatment processes that eliminated stress-related concerns. Most importantly, they demonstrated that semi-skilled workers could produce acceptable welds after just 2 weeks of training. Production jigs positioned every piece perfectly, allowing consistent results from relatively inexperienced welders. By March 1941, component production was underway across multiple Chrysler facilities. The tank scheduled to roll out in April would be assembled from parts manufactured in Detroit, Highland Park, and supplier locations throughout Michigan and neighboring states. The engine situation required creative problem-solving that would produce one of the war's most unusual power plants. The M2A1 used the Continental R975 radial aircraft engine, producing 400 horsepower. Reliable and proven, but Continental couldn't increase production fast enough. Chrysler needed an alternative engine solution immediately. The answer came from engine designer Harry Wilson, working with Chrysler's powertrain engineering team. Chrysler had been developing a new inline 6-cylinder engine, producing 115 horsepower for automotive applications. Wilson proposed combining 5 of these engines into a single tank power plant. The concept seemed mechanically absurd. Linking 5 separate engines to drive a single output shaft created enormous engineering challenges involving gear ratios, synchronization, and mechanical complexity. But Chrysler engineers embraced challenging problems as opportunities for innovation. Under Wilson's direction, they created what would become the A57 multibank engine, the most unusual tank power plant ever manufactured. The A57 used 5 complete inline 6-cylinder engines, arranged in a circular pattern around a central gear case. Each engine drove an individual gear that meshed with a central output gear. The entire assembly produced 425 gross horsepower from 30 cylinders displacing 1,253 cubic inches. The design was bizarre, mechanically complex, and completely unprecedented in military applications. It was also absolutely brilliant for mass production requirements. The multibank engine solved multiple problems simultaneously using existing components and tooling. Production could begin immediately without developing new manufacturing processes. Assembly required no exotic materials or specialized equipment unavailable to civilian industry. Relatively unskilled workers could assemble engines following clear procedures and quality control specifications. Military engineers hated the multibank concept on principle, calling it a Rube Goldberg contraption that violated established military engineering practices. But they couldn't argue with production timelines and delivery schedules. April 12, 1941, arrived with Detroit, experiencing an unusually warm spring day. One day before Easter Sunday, families throughout Michigan prepared for religious celebrations and the promise of warmer weather after a brutal winter. The Detroit Arsenal tank plant remained visibly unfinished. Portions of the massive building still lacked exterior walls. Windows were absent throughout large sections. The heating system remained incomplete, requiring continued use of the steam locomotive for worker comfort. But on the assembly line floor, surrounded by construction equipment and unfinished building systems, sat the first Chrysler-built M3 medium tank, complete and ready for Army acceptance. The M3 represented evolutionary development from the M2A1 design. It mounted a larger 75mm main gun in a hull-mounted sponson, plus a 37mm gun in a fully rotating turret. The design was already recognized as transitional, a compromise between proven technology and urgent military necessity. But this particular M3 represented something far more significant than another tank design. It was the first tank ever produced using automobile-style assembly line methods. The first tank manufactured with precision components requiring no hand-fitting during assembly. The first tank that proved American industrial genius could revolutionize military production through mass manufacturing techniques. Formal delivery ceremonies occurred 12 days later, on April 24, 1941. The completed M3 was driven from the still unfinished factory before an assembled crowd of military officials, Chrysler executives, local politicians, and hundreds of workers who had made this achievement possible. Keller rode inside the tank as it emerged into brilliant spring sunshine. The demonstration that followed was carefully choreographed to impress skeptical military observers who still doubted mass production methods could produce combat-worthy vehicles. The 28-ton M3 accelerated across the proving ground, crushing obstacles and demonstrating mechanical reliability. Main gun and machine gun systems were fired repeatedly without malfunction. The tank smashed through a mock farmhouse construction, obliterating the structure completely. What the public demonstration didn't reveal was far more significant than what spectators witnessed. Behind that single completed tank stood a production system unlike anything the military world had ever seen or imagined possible. The assembly line was now fully operational with workers trained and equipment calibrated. Component production was accelerating throughout the supplier network. Hundreds of workers were mastering specialized tasks that would enable unprecedented production rates. May 1941 witnessed production increase to 1 tank every other day. By June, daily tank completion became routine. July brought 2 tanks rolling off the line each day. August saw 3 tanks daily, with 4 tanks achieved by September. Chrysler simultaneously developed the supplier network required for sustained mass production. A single tank demanded approximately 8,000 individual components. Chrysler couldn't manufacture everything within company facilities without massive additional investment. B. Hutchinson led supplier development efforts, traveling throughout Michigan, Ohio, Pennsylvania, and neighboring states. His sales pitch was direct and compelling. We need these specific parts manufactured to these exact specifications in these precise quantities delivered on this rigid schedule. Can your company meet these requirements? Many suppliers initially balked at the demanding specifications and delivery schedules. But Hutchinson offered valuable incentives, including technical assistance, advance payments for required tooling, and guaranteed long-term contracts. The supplier network expanded throughout 1941, eventually encompassing over 400 companies across 32 states. A foundry in Pennsylvania produced final drive housings to exact specifications. Machine shops in Wisconsin manufactured track pins and suspension components. Forge operations in Ohio supplied armor plate blanks. Each supplier became part of a coordinated network, delivering components to precise schedules that kept assembly lines operating without interruption. Workforce transformation paralleled supply chain development throughout 1941. June 1940 found Chrysler employing exactly 0 workers with any tank manufacturing experience. By August 1941, the Detroit arsenal employed 5,800 workers, most learning specialized tank assembly operations from complete scratch. Chrysler established comprehensive training schools where new employees learned specific operations before moving to production floor assignments. A worker assigned to transmission installation spent 2 full days practicing on training fixtures before touching an actual production tank. This systematic approach allowed rapid workforce expansion with minimal productivity loss during learning periods. Workers achieved competency quickly because each performed limited specialized operations rather than complex assembly requiring broad mechanical knowledge. By September 1941, the Detroit arsenal was producing 4 tanks daily with consistent quality and reliability. The M3 medium tank was proving its combat worth in North African desert campaigns, where British units received American tanks through lend-lease arrangements. British tank crews nicknamed the M3 the Grant after Civil War General Ulysses S. Grant. They appreciated its mechanical reliability and powerful armament, though they criticized its excessive height and hull-mounted main gun that limited firing traverse. Chrysler engineers were already developing the M3's replacement, using lessons learned from initial production experience. The Tank Committee had recognized from the program's beginning that the M3 represented transitional technology rather than optimal tank design. The hull-mounted main gun created unnecessary vehicle height and limited tactical flexibility. A superior design would mount the primary weapon in a fully rotating turret providing complete traverse and improved crew protection. Working closely with Army Ordnance engineers, Chrysler developed what would become the M4 Sherman tank, the most iconic and widely produced American tank of World War II, incorporating production lessons learned from M3 manufacturing experience. The shift from M3 production to M4 manufacturing revealed something remarkable about modern industrial systems. Instead of grinding operations to a halt for complete retooling, the Detroit arsenal demonstrated unprecedented flexibility. Production lines adapted gradually. M4 components slowly replaced M3 parts. Workers learned new procedures while completing existing contracts. The transition flowed like water, finding a new channel. By February 1942, only Sherman tanks emerged from the assembly line. The M4 Sherman represented a revolution in military design philosophy. Every bolt, every plate, every component reflected one core principle. Mass production came first. Traditional tank design started with military requirements. Engineers then figured out how to build what generals wanted. The Sherman reversed this approach completely. Chrysler engineers examined each design element through manufacturing eyes. Could this be cast quickly? Could that be welded efficiently? Did these parts require hand fitting? The answers shaped every decision. Hull construction exemplified this thinking. Large castings eliminated dozens of smaller components. Welded sections reduced assembly time. Complex curves that required skilled metalworkers disappeared. The design prioritized speed over elegance, function over tradition. The turret emerged from specialized foundries as single castings. No assembly required, no fitting needed. Just mount and move forward. Drive trains used standardized components throughout. Parts interchanged between different tank models. Maintenance became simpler. Supply chains streamlined. Even track design reflected production thinking. Links could be manufactured rapidly. Assembly required minimal skill. Replacement happened quickly in field conditions. Then Pearl Harbor changed everything forever. December 7, 1941, shattered American complacency. The Japanese attack transformed cautious preparation into desperate urgency. Army tank requirements exploded overnight. The 1,000 tanks that seemed ambitious in 1940 became laughably inadequate by early 1942. National survival demanded industrial miracles. Chrysler responded with characteristic determination. The facility that had struggled to produce 4 tanks daily in September 1941 was delivering 12 tanks daily by March 1942. Workers arrived earlier, shifts extended longer, suppliers accelerated deliveries. The entire operation pulsed with new intensity. By July, 18 tanks rolled off the line each day. This acceleration created cascading challenges. Bottlenecks appeared like mushrooms after rain. Different operations fell behind at unpredictable moments. Solutions required constant creativity. Qualified welders became critically scarce. Hull production slowed to frustrating crawls. Traditional apprentice programs took years to produce skilled operators. The war wouldn't wait for traditional training. Chrysler established intensive welding schools. 50 trained operators graduated weekly. Classroom instruction condensed months of learning into intensive weeks. Practice sessions ran around the clock. Machine tool shortages threatened component production. Specialized equipment required months to manufacture. Delivery schedules stretched into following years. Chrysler engineers worked directly with machine tool manufacturers. They arranged priority deliveries. They modified existing equipment for new purposes. They designed workarounds for missing capabilities. Owen Skelton received promotion to General Manufacturing Manager. He established systems called production expediting. Teams of engineers prowled the production floor constantly. They monitored every operation. They identified bottlenecks within hours rather than weeks. Solutions arrived within days rather than months. Problems couldn't hide in this environment. The culture transformed completely. Numbers dominated everything. Daily production totals appeared on prominent bulletin boards. Workers knew exactly how many tanks had been completed that day, that week, that month. Information flowed freely throughout the facility. Everyone understood their contribution to overall success. Competition emerged naturally between shifts. Day shift challenged night shift. Night shift responded with determination. Each group pushed to exceed the other's production totals. Friendly rivalry became fierce motivation. Personal pride merged with national purpose. December 1942 witnessed something many experts had claimed was impossible. 896 Sherman tanks rolled off the assembly line that month. 29 tanks per day. This single facility was outproducing entire national tank industries. The Detroit arsenal alone exceeded all German tank production combined. The achievement resulted from relentless optimization. The assembly line operated with mechanical precision that would have impressed Henry Ford himself. Tanks moved from station to station every 55 minutes. Workers had refined their operations through months of repetition. Muscle memory replaced conscious thought. Hands moved automatically to correct positions. Suppliers delivered components with clockwork reliability. Inventory could be minimized without risking production delays. Storage space became assembly space. Efficiency compounded upon efficiency. Quality control evolved into precise science. Inspectors checked dimensions and fit at every stage. Defects were caught immediately rather than discovered later. Rework became rare rather than routine. The 896 tank month represented the absolute peak of wartime production efficiency. Later months sustained high production levels, but December 1942 remained the single-month record for the entire war duration. It proved that tank production had been completely transformed. From craft work to industrial process, from art to science. Success created new demands. The Army wanted additional tank production capacity distributed across different geographic regions. Enemy bombing couldn't destroy all facilities simultaneously. Several new tank plants were constructed rapidly. General Motors operated one facility. Pressed Steel Car Company managed another. Pacific Car and Foundry built tanks on the West Coast. Each plant adopted assembly line approaches and precision manufacturing methods pioneered at Detroit Arsenal. But the original facility remained unique in production volume and operational efficiency. No other plant matched its output. None exceeded its productivity improvements. By war's end in August 1945, the Detroit Arsenal had produced 22,234 tanks of various models. This represented approximately 25% of all American tank production during World War II. One facility, 1/4 of national output. The mathematics spoke for themselves. The tanks themselves continued evolving throughout production. The Sherman went through multiple variants. Each incorporated specific improvements. The M4A1 featured a cast hull for improved protection. The M4A2 used twin diesel engines. Fuel efficiency increased significantly. British and Soviet forces preferred diesel models for logistics reasons. The M4A3 mounted the Ford GA V8 engine. Reliability improved markedly. The M4A4 used the Chrysler A57 multi-bank engine. Power increased substantially. Each variant required production line modifications, yet the basic assembly process remained constant throughout all changes. This flexibility provided another crucial advantage. Traditional craftsman production required rebuilding entire skill sets for each design change. Masters had to relearn their craft. Apprentices started over completely. Assembly line production simply required modifying fixtures and updating work instructions. Changes happened in days rather than months. The Sherman's combat reputation has been endlessly debated by military historians. It was inferior to German tanks like the Tiger and Panther in armor protection and gun power. Sherman crews faced terrifying odds in direct combat with these heavier vehicles. Individual tank duels often ended badly for American forces. But the Sherman possessed advantages that mattered more in the strategic aggregate. It was remarkably reliable. Operational readiness far exceeded German tank performance. Complex German designs broke down frequently. Repairs required specialized parts and highly trained mechanics. Shermans kept running under conditions that disabled enemy vehicles. Repair was straightforward and quick. Standardized components meant parts availability everywhere. Well-trained maintenance crews could fix problems rapidly. Battle damage that would total a German tank could be repaired overnight on a Sherman. Availability trumped individual superiority. Above all, Shermans existed in overwhelming numbers. Production mathematics told the real strategic story. Germany produced approximately 24,000 main battle tanks from 1939 to 1945. 6 years of total war effort. The Soviet Union built approximately 105,000 tanks in the same period. Massive industrial capacity dedicated to tank production. Britain managed about 28,000 tanks total. Respectable output for a smaller industrial base. The United States, entering large-scale production only in 1942, built approximately 88,000 to 90,000 tanks by 1945. 3.5 years of production exceeded 6 years of German output. The Detroit Arsenal alone produced roughly 1/4 of American tank output. But raw numbers tell only part of this transformation story. The real revolution was in how tanks were produced. Before 1940, every major power treated tank manufacturing as specialized military work. Government arsenals employed craftsmen with years of experience. Production remained limited by skilled labor availability. After Detroit Arsenal, tank production became understood as industrial work. Engineering skill and production expertise mattered more than military tradition. This philosophical shift carried profound implications for modern warfare. Production could be scaled rapidly by engaging private industry. Workers could be trained in weeks rather than years. Supply chains could be distributed across entire continents. Production capacity could be maintained even as experienced workers entered military service. Young women replaced men called to combat. Farmers learned precision manufacturing. Recent immigrants operated complex machinery. The workforce democratized completely while productivity soared. World War II ended, but the Detroit Arsenal continued operating under government contract. Tank production ceased temporarily during peacetime conversion. The Korean War brought renewed urgency. From 1952 to 1954, the facility produced 3,447 Patton tanks. Assembly lines roared back to life. Workers returned to familiar routines. During the 1960s, M60 tanks emerged from the same production lines. Technology advanced, but manufacturing principles remained constant. In 1979, the facility began producing components for the revolutionary M1 Abrams. Cutting-edge technology met proven production methods. Financial pressures mounted during the early 1980s. Chrysler faced severe economic challenges across all divisions. In 1982, the company sold its defense division to General Dynamics for $336.1 million. New ownership continued tank production traditions. General Dynamics operated tank production at the Arsenal until 1996. Industry consolidation shifted operations to the Lima Army Tank Plant in Ohio. The Detroit era ended after more than half a century, but the legacy lived on in new facilities using identical principles. The Detroit Arsenal site today hosts different military functions. The United States Army Tank Automotive Life Cycle Management Command operates from the location. The Combat Capabilities Development Command Ground Vehicle Systems Center continues research and development work. A Michigan historical marker commemorates the site's remarkable role. It notes that more than 22,000 tanks were produced here. American industrial might had been successfully weaponized. Key figures from the story experienced varying post-war fates. Kaufman Thuma Keller continued leading Chrysler through the challenging war years. He became chairman in 1950 after proving his leadership during the crisis. Retirement came in 1956 after transforming the company completely. Albert Kahn died on December 8, 1942, just months after the Detroit Arsenal reached peak production levels. His architectural innovations influenced industrial construction throughout the 20th century. Factory design principles he established remain standard practice today. William Knudsen served throughout the war as Lieutenant General in the United States Army. His commission came January 28, 1942. This represented the highest rank ever given to someone not already in military service. He died in 1948, having bridged civilian industry and military necessity. Sherman tanks built at Detroit Arsenal served in every theater of World War II. They landed on Normandy beaches during D-Day operations. Crews drove them across France and into Germany. They island-hopped through the Pacific with Marine Corps units. International allies operated them under Lend-Lease agreements. British forces used Shermans in North Africa and Europe. Canadian units preferred them for reliability and maintenance simplicity. Free French forces operated them during liberation campaigns. Soviet armies received thousands through Arctic convoys. Chinese forces used them against Japanese occupation troops. Many Shermans survived the war, and continued serving for decades afterward. Israel modified Shermans extensively for the 1967 Six-Day War and 1973 Yom Kippur War. Improved armor and guns kept them competitive. South American nations operated Shermans into the 1980s. Reliable mechanical systems outlasted more sophisticated designs. A few remain in running condition today. Museums preserve them as monuments to an era when industrial capacity determined military power. Restored examples still rumble across parade grounds. Living reminders of mass production warfare. The transformation of tank manufacturing from craft to industry happened because engineers and industrialists refused to accept conventional wisdom. They recognized no fundamental difference between assembling automobiles and assembling tanks. Both were mechanical devices built from thousands of components. Both could be manufactured on moving assembly lines by specialized workers performing specific operations. This insight seems simple in retrospect, but it was revolutionary in 1940. Looking past surface differences to see underlying similarities required exceptional vision. Engineering courage was needed to redesign military equipment despite military resistance. Industrial confidence was essential to commit to production methods never attempted at such scale. The Detroit Arsenal's success validated Henry Ford's earlier insights about mass production while extending them into entirely new domains. Ford had proved that interchangeable parts and moving assembly lines could produce automobiles at unprecedented volume and dramatically reduced cost. Chrysler proved these methods could produce instruments of war with equal efficiency. This possibility transformed World War II's ultimate outcome. Without mass-produced tanks, American ground forces would have fought at severe numerical disadvantage throughout multiple theaters. Britain would have struggled desperately to replace combat losses. The Soviet Union benefited enormously from thousands of American-made Shermans. The ability to produce 88,000 to 90,000 tanks in 4 years was unique to American industrial capacity. Roughly 1/4 came from a single facility in Warren, Michigan. The invisible achievement was perhaps greater than the visible one. The Detroit Arsenal didn't just build tanks efficiently. It proved a revolutionary concept about government and private industry relationships. It demonstrated that private companies could solve government problems faster and more efficiently than government could solve them itself. It showed that engineering expertise mattered more than military tradition in production situations. It validated the idea that American industrial capacity, if properly mobilized, represented a war-winning advantage that no enemy could match. This validation shaped post-war American strategy fundamentally. The concept of maintaining industrial capacity that could be rapidly converted to military production became central to Cold War planning. The idea that American industry could outproduce any potential adversary became established doctrine. The relationship between private contractors and military procurement that began with the Detroit Arsenal contract became permanent governmental structure. The engineers who made the Detroit Arsenal possible were practicing systems thinking decades before the term existed in management literature. They didn't just solve individual problems in isolation. They designed entire systems where components, suppliers, workers, assembly processes, and quality control functioned as integrated wholes. Each element was optimized not independently, but as part of the larger production system. This systematic approach was visible in countless operational details. The assembly line's sunken trench eliminated bottlenecks in undercarriage assembly operations. The supplier network created resilience by distributing production across geography and multiple companies. The training system created a pipeline of skilled labor that could replace losses and support expansion. Every element was designed to scale efficiently. When production needed to double, the system could absorb increases by adding shifts, expanding supplier orders and training more workers. When new tank variants were introduced, the system could adapt by modifying fixtures and updating procedures. Flexibility was built into every component. The ultimate measure of success was continuous efficiency improvement over time. The first M3 tank, built in April 1941, required approximately 500 man-hours of direct labor. By December 1942, M4 Shermans were being built in approximately 150 man-hours. This productivity improvement of more than 300% came from relentless optimization efforts. Every month, engineers studied production data meticulously. They identified operations taking too long or producing defects. They analyzed why workers struggled with particular tasks. They redesigned fixtures or procedures based on actual experience. They questioned every decision constantly, asking whether there was a faster, simpler, better way to accomplish the same result. This culture of continuous improvement, borrowed from civilian automotive production, was completely alien to military arsenals, accustomed to unchanging procedures handed down through generations. But it was absolutely essential to achieving the production volumes that modern warfare demanded. Innovation became routine rather than exceptional. The financial cost was substantial but modest compared to total output value. The facility's initial construction cost approximately $20 million. Equipment and tooling added another $30 million. By war's end, total investment exceeded $100 million, but the 22,234 tanks produced represented a value exceeding $2 billion. The return on investment was enormous by any financial measure. More significant than financial return was strategic value creation. The Detroit Arsenal's production capacity allowed American ground forces to fight with numerical superiority in armored vehicles throughout multiple theaters. This advantage was crucial in campaigns from North Africa to Germany. Without the production capacity created at Detroit Arsenal and similar facilities using identical methods, World War II's outcome might have been dramatically different. Industrial capacity proved as decisive as military strategy or tactical innovation. The story of the Detroit Arsenal is ultimately about seeing possibilities that others completely missed. When Keller told Knutson he had never seen one of these things, he was acknowledging ignorance, but not inability. Chrysler's engineers didn't know how to build tanks initially, but they knew how to build complicated mechanical assemblies from thousands of components efficiently. This confidence that engineering could solve any production problem was characteristically American in its optimism. European manufacturers accepted that tanks were inherently different from civilian products, requiring specialized facilities and traditional craftsman skills developed over generations. American industrialists saw only machines, all of which could be broken down into components, processes, and assembly sequences. The Detroit Arsenal validated this philosophy completely and dramatically. In 9 months, Chrysler went from zero tank production to delivering finished vehicles regularly. In 18 months, they were producing tanks at rates that exceeded military requirements. In 3 years, they had delivered more tanks than most nations produced in the entire war. The engineers and workers who made this achievement possible were ordinary people doing extraordinary work under exceptional circumstances. They weren't heroes in the conventional military sense. They didn't storm beaches or liberate concentration camps directly. But they built the tools that made those achievements possible. This contribution was equally vital to victory. This democratization of military production was itself revolutionary in warfare history. In previous wars, weapons came from specialized arsenals operated by master craftsmen with decades of experience. Production was always limited by the availability of highly skilled labor. Training took years to complete. In World War II, American weapons came from automobile factories and dozens of civilian industries that converted to military production rapidly. The workers were housewives, recent high school graduates, farmers, and shop clerks who learned specific operations and performed them repeatedly with precision. The Detroit Arsenal was both symbol and proof of this fundamental transformation. It showed that private industry could build military equipment more efficiently than government arsenals using traditional methods. It demonstrated that production methods developed for civilian goods could apply successfully to weapons of war. It validated the arsenal of democracy concept that Roosevelt had articulated. And it established that in modern warfare, industrial capacity was as important as military strategy or tactical brilliance. Production won wars as decisively as battles. Today, most people driving past the site have no idea what extraordinary events happened there. But the legacy persists in less visible ways throughout modern manufacturing. The M1 Abrams tank is built using production methods descended directly from those developed at Detroit Arsenal. Modern military manufacturing relies heavily on private contractors using industrial production techniques. The integration of supplier networks, precision manufacturing, and assembly line production that Chrysler pioneered remains standard practice across defense industries worldwide. The transformation from craft to industry that began on those 113 acres in Warren, Michigan, fundamentally changed how nations equipped their militaries. It proved that engineering expertise could solve seemingly impossible problems by refusing to accept conventional limitations as permanent barriers. It showed that production principles could apply to the most complex military equipment successfully. And it demonstrated that American industrial capacity, when properly mobilized and systematically organized, could produce the tools of victory in quantities that completely overwhelmed any adversary. This was the invisible weapon that helped win World War II decisively. Not superior technology alone, though that mattered significantly. Not better tactics exclusively, though those were important. Not more natural resources simply, though those were crucial. The decisive advantage was the ability to treat war as an industrial problem and solve it systematically with proven industrial methods. Kaufman Thuma Keller, answering that telephone call on June 7, 1940, couldn't possibly have imagined where his honest admission would ultimately lead. But in saying he didn't know but would figure it out, he articulated the confidence that made victory achievable. The engineers who designed the production system, the workers who operated it daily, and the suppliers who fed it continuously were all engaged in a collective achievement that changed warfare itself permanently. They proved that tanks could roll off assembly lines exactly like automobiles. They showed that mechanical complexity was no barrier to mass production when properly approached. And they demonstrated that American industrial genius, when properly challenged and systematically organized, could accomplish what military tradition insisted was completely impossible. The story deserves to be remembered not just for what was produced in impressive quantities, but for how production itself was fundamentally transformed. The Detroit Arsenal wasn't simply a tank factory producing military vehicles. It was proof that systematic engineering thinking could solve any problem if the right people asked the right questions and refused to accept that impossible meant anything more than not yet attempted. The tanks are mostly gone now, scrapped for metal, or preserved in museums as historical artifacts. The factory has been largely demolished and replaced with different structures. The workers have passed away, taking their memories with them. But the method remains alive and vital. The insight that complicated mechanical assemblies can be mass-produced regardless of their intended purpose survives in every modern factory worldwide. And the confidence that engineering can solve production problems systematically lives on in every industrial designer who looks at a complicated product and asks not "can we build it?" but "how can we build it efficiently, reliably, and at massive scale?" That question, asked and answered definitively at the Detroit Arsenal between 1940 and 1945, changed the world permanently. It made mass-produced warfare possible for the first time. It validated American industrial methods as superior to European craft traditions. It proved that private industry could outproduce government arsenals consistently. And it showed that when engineers are given impossible problems, they sometimes solve them by refusing to recognize impossibility as a permanent condition. This is why the story matters fundamentally. Not because tanks are inherently interesting, though they certainly are. Not because World War II is historically important, though it unquestionably was, but because the Detroit Arsenal represents a way of thinking about problems that remains powerfully relevant today. See the underlying similarities, not just the surface differences. Apply proven methods to entirely new domains confidently. Design complete systems, not just individual components. And never accept that something cannot be done simply because it has never been done before. In 9 months, Chrysler went from never having seen a tank to producing them efficiently on assembly lines. In 18 months, they were exceeding all expert expectations dramatically. In 4 years, they built more tanks than most entire nations produced throughout the war. This was possible because engineers looked at a military problem and recognized an industrial challenge. They refused to be constrained by tradition, convention, or expert pessimism. They identified the real problem and solved it systematically. That remains the most important legacy today. Not the thousands of tanks it built, impressive though that achievement was, but the proof it provided that engineering confidence, industrial capability, and systematic thinking can accomplish what initially seems completely impossible. When someone declares it cannot be done, the right answer remains, show me why not, and let us figure it out together. That answer, applied consistently and confidently by dedicated people, built an arsenal that helped save democracy itself. This lesson deserves remembering and applying whenever impossible problems demand solutions.